We'll now continue our coverage of the role of mutable state in modern Java programs. In particular, we'll describe the benefits of applying shared mutable state to implement a memoizing cache. We'll also explain what a memoizing cache is. And then finally, we'll explore the Java-based design and implementation of the Memoizer class, which shows how shared mutable state can be used to optimize the performance in modern Java programs. We'll start by giving an overview of how memoization works. Memoization is an optimization technique that can be used to speed up programs through the use of shared mutable state. Memoization typically uses an atomic check-then-act operation to cache the results of expensive function calls. The pseudocode on this slide shows the signature and semantics of a typical method that implements memoization. This method is called compute if absent. It takes a key and a function. If the key doesn't exist yet in the cache, the compute if absent method performs a long-running function associated with the key and stores the resulting values in the cache using the key. It then returns the value that's been associated with the key in the cache. Henceforth, when the same inputs occur again, the cached results are simply returned. For example, if the key already exists in the cache, that cached value associated with the key is returned without performing the long-running computation again. We'll now discuss the design of a Java Memoizer class. The Memoizer class we'll discuss defines a cache that uses shared mutable state to optimize performance in concurrent programs. The Memoizer class is based heavily on the excellent book Java Concurrency in Practice by Brian Getz and his colleagues. The Memoizer constructor is passed a function. This function is stored in the mfunction field. The Memoizer later uses this function to produce a value based on a key. It does this by calling the get method, passing in the key. If the key has no value associated with it yet, then get uses mfunction to compute the value and stores it in the cache. If the key already has value associated with it, however, then get simply returns that value, rather than using the mfunction field to recompute it. This use of shared mutable state helps to optimize performance by caching the results of long-running functions. Internally, Memoizer uses a concurrent hash map stored in the mcache field to minimize synchronization overhead in concurrent programs. Concurrent hash map supports full concurrency of get calls and high expected concurrency for put calls. Moreover, contention in a concurrent hash map is very low due to the use of multiple locks, essentially one for each bin in the hash table, as described in the link at the bottom of this slide. In contrast, contention is much higher in other Java synchronizers, such as Java's synchronized map, which only has a single lock. Internally, the get method of Memoizer uses the concurrent hash map method compute if absent to ensure that the m function is called only once when a key is first added to the cache. In turn, the concurrent hashmap compute if absent method uses atomic check-then-act semantics to ensure that only one m function call occurs if multiple threads simultaneously invoke it for the same key at the same time. Now that we've given an overview of the Java Memoizer class, let's walk through its implementation. You can find this implementation in the memoizer.java class at the link at the bottom of the slide. So we're now in my IntelliJ project for case study EX3, and we're first going to take a look at the Memoizer class. And this class defines a so-called memoizing cache that demonstrates how shared mutable state can be used to optimize the performance of a concurrent Java program. And an instance of Memoizer is used to map a key to the value produced by a function argument that's passed to its constructor. And the virtue of this is if the value has previously been computed, it's returned rather than calling the function to compute it again. You'll see that we use a Java concurrent hash maps compute if absent method to ensure that there's only a single call to the function when a key and value are first added to the map, even when the Memoizer is used in a concurrent and/or parallel program. And this particular bit of code is inspired by an example in the book Java Concurrency in Practice by Brian Getz and his colleagues. And you can find more information about memoization at this link. So as you can see, Memoizer is a generic Java class that's parameterized by a key and a value type, which we call K and V here. And it defines a couple of fields that are essential for its implementation. The first field is called mcache, and this is a map that associates a key K with a value V that's produced by a function. And that function is stored in the second field here called mfunction, and this function produces a value that's based on the key. So let's now take a look at how those fields are initialized in the Memoizer constructor. You can see that the function parameter is passed in here, it's stored in mfunction, and we go ahead and create a new concurrent hash map and store it in the mcache field. The key method in this class is called get, and it returns the value that's associated with the key, which is passed as a parameter. If there's no value associated with the key at all, the function that was registered in the constructor is called to create the value and store it in the cache before it's returned from get. And you can take a look at the get implementation down here. It uses the concurrent hash maps compute if absent method. And this is a very special method. It performs what's called atomic check then act semantics. It will look and see if there's already a value associated with the key in the map, and if so, it'll return it. But if there is no value that's associated with the key in the map, then the mfunction is atomically called to compute the value, which is then stored in the map, and then that value is returned. And all those operations occur atomically, such that if multiple threads of control simultaneously call get for the same key that's not in the map, that function is only called one time, not multiple times. There's several other methods in the Memoizer class. The remove method simply removes the key and, of course, its corresponding value from the Memoizer. So if there's no value that's associated with the key, in other words, if key has not been stored in the map previously, then nothing happens. And the final two methods here simply return the number of entries in the cache and also return the map that's used to implement the cache if you need to do something to it, for example, to clear it out. So that's a quick walkthrough of the Memoizer class. As you can see, this is demonstrating the use of shared mutable state, and then we'll shortly see how this can be applied in the context of a concurrent Java program to demonstrate how shared mutable state can optimize the performance of that concurrent program. Now that we've walked through the implementation of the Memoizer class, let's wrap up this lesson on the role of mutable shared state in modern Java. Although there are situations where shared mutable state is helpful and necessary, such as the Memoizer example we looked at, you're generally much better off by minimizing and/or avoiding the use of shared mutable state in your programs, if at all possible. If your Java programs must use shared mutable state, make sure to add the necessary synchronizers and/or use the appropriate concurrent or synchronized collections. There's a wide range of these synchronizers and/or collections, which are summarized on this slide. This YouTube playlist has extensive coverage of Java concurrent collections and synchronizers. So that's the end of part 2 of our discussion on the role of mutable state in modern Java programs.